Welcome back, everyone. Okay, so we left off in we've done the post ordering of the tree. Okay, and this is so now we have this post-ordered elimination tree, and this is going to be very important now for figuring out the rest of the algorithm. There's a lot of the theorems that our algorithm is going to depend on that require the tree to be post-ordered. Now, you don't actually have to take the matrix A. You're factoring A, the matrix A. Normally, it's not going to come to you in post-ordered form. Okay, so you find the tree, do the post-ordering. That induces a permutation on the matrix C, but you can always, you remember I talked earlier about looking at a matrix through a lens, right? You can have this matrix unpermuted, and you can just sort of have a little lens in front of it that's a set of permutation vectors that when you grab an entry from the matrix, you just flip it around, and now you get the new one. So you don't have to actually compute this permutation explicitly. You can just do it on the fly. Anyway, so this is the post-ordered matrix, and it has the same elimination tree, just with different node numbers. And then all these theorems then are going to depend on that post-ordering. So remember where we're looking. The whole goal here is we're looking at these row subtrees. They're subtrees of this elimination tree. Now, remember, they're not necessarily complete subtrees in the sense that you pick a node and normally a subtree would be everything below it. But the row subtrees are going to stop early. They're going to stop at leaves that correspond to non-zeros in the original matrix C. So if you go down here, if say 5 is not a non-zero in the 9th row, okay, then it won't appear. In fact, it's not. So right here, the 9th row subtree will just be these three nodes, see? 7, 8, and 9. Because 5 and 6 are 0 here. They don't appear. So it's row subtrees that are important because for several reasons, but one of them is we want to figure out how many non-zeros there are in each row, and it's just the size of this tree. So the gist of this algorithm we're going to come up with here is this tree is characterized by its leaves. So there is a tree with TK, which I've drawn circles for every node representing a non-zero in the kth row of the A matrix. So there's 6 of them, but only 4 are of importance. And those are these at the bottom, the skeleton, the entries in the skeleton matrix. Now, of course, just as I showed here, these might be roots of subtrees in the entire elimination tree, but we're not considering them. We're not interested in those right now because we only want the kth row subtree, a very special subtree. So to do this, we're going to use some, as I mentioned, path decomposition. I want to break this tree implicitly into these paths like that. Going left to right, it's formed by the first leaf going all the way to the root, and then subsequent leaves going up until you've seen a node you've seen before. Okay, and then if we can rip that tree apart with those disjoint paths, we just sum up the length of the paths, and we're done. But to do that, we need to. It's a long way. We don't want to actually traverse this path to find this decomposition. Okay, that's the magic of the algorithms that are coming next. I'm not just going to walk up this and go touch, mark all those nodes and walk here and say, oh, okay, I'll stop and so forth. That's too expensive. We're not going to do that. I'd like to do it faster than that. So to do that, I need to compute. We need to compute two things. We need to compute the first descendant, and we need to compute the level of each tree. And so this next algorithm is going to do that. I'll just pull the code up. So here's the code. The idea is very simple. Okay, if you have a tree, let's remember now we're dealing with the post-ordered tree. So I'm going to just write up here the post-ordered tree repeated, and I'll just mimic this algorithm so you'll see how it works. This algorithm is very straightforward. The other ones that we're going to come across are much more subtle. They involve, again, this disjoint set union find thing. Remember that funny thing about following paths and ancestors and all that we did for the elimination tree? We've got the elimination tree now. We're going to use that idea again right here. But not in this algorithm, next algorithm. This algorithm is simple. So this should be really, well, they should all be clear, but this one should be crystal clear. So I want to find the first descendant of each node. The first descendant is my lowest, if you will, my youngest grandchild, okay, my youngest descendant, the descendant that is numbered the least. And so the least, including myself. So I might be my own descendant, which sounds like a country music song, right? I'm my own grandpa. Have you heard that song? If you're not from the United States, you wouldn't have heard it, which is a very good thing, actually, not to hear this song. So I won't sing it for you. So 1 is its own least ancestor. Descendant, I'm sorry. It's its own grandpa. Okay. The least descendant of 2 is 1. The least descendant of 3 is 3. The least descendant of 4 is 1. If you look at all the descendants of 4 and look at what's the one that's numbered the least, it's 1. So is 10. 10 is the least is 1. The least of 11 is also 1. But the least of 9 is, the least of, well, 5 is 5. The least of 7 is 5. The least of 8 is 5. The least of 9 is 5, and so forth. The least of 6 is 6. But as I started writing those numbers down now, do you see the algorithm? The idea is then to find the least ancestors. We start off by saying no one knows who their least ancestor is. So we mark all these nodes as empty or unknown. So -1 is what I use in this algorithm. So nobody knows their first ancestor. Descendant. I'm sorry. My dyslexia is acting up today. Nobody knows their first descendant. Your first ancestor is your parent, I guess. That's easy. Unless you're adopted. And you may not know your parent. But everybody here knows their parent. So we're going to go across each node in the post-ordered version, okay? Because remember, we're not actually necessarily working with a tree that is intrinsically post-ordered. We have a post-ordering and the original tree. We don't necessarily want to permute the matrix according to that permutation. I mean, for example, what if in MATLAB you're just asked to, and this happens to me all the time, right? You just say, well, I mean, give me the Cholesky factorization of that matrix. That's it. And then A is equal to LL transpose. You don't have the freedom to go and permute the matrix. All right. So we can't just arbitrarily permute the matrix. But if you want to ignore this statement here, I equals post of K, you can do that and just imagine that you're working with a tree that's already intrinsically post-ordered. Then I and K would be identical. So it would be an identity permutation here. So all we have to do is start at the node 1 and walk this whole path explicitly until we come across either the root or a node that already knows its first descendant. And we just mark this with this node number 1. Because if these nodes haven't been seen yet, and I have a path from here to the root, then, well, number 1 must be, it's the lowest number, right? And these are all my ancestors, and so I must be their descendant, and I'm number 1, so, well, obviously these first descendants, the least number descendant is 1, because 1's the smallest number. There. So we've just found the first descendant of 5 nodes. Now we go to node 2 and ask, well, do we need to do the same process? No. Because 2 and its ancestors already know who their first descendant is. It won't be 2. It'll be somebody less than 2. It happens to be 1. So now we go to the third node, node 3. Okay, node 3. Oh, node 3 doesn't know its first descendant. So it's its own first descendant. And we start walking up the tree, and we've come to node 4. Node 4 already knows whose its first descendant is, and so does thus all of its ancestors. That's this loop invariant here. If node 4 knows who its first descendant is, that first descendant must be less than 3, because I haven't given anybody known first descendants bigger than 3 yet. They're all less than 3. So whatever this is, it's number 1. That's going to be less than 3. I don't even have to look at it. I know it's going to be less than 3. So if I come to a node that already knows its first descendant, I just stop. Because if I go up here and say, well, I mean, imagine you could do the following. Okay, imagine you could say, well, I have a node, and here are all my ancestors. And so if I am node K, maybe I shouldn't use K because K is over there. If I'm node T, then I could go up here and make sure that the first ancestors of all these nodes is less than or equal to T, because I know I'm a descendant of everybody in this chain. So I could just reset these to the minimum of T and the currently known first descendant. And that'll suffice for node T. But there's no point. Once we stop here, once we come to the node that knows its first descendant, everybody above it knows its first descendant, and it's not going to get any smaller than T because these are all going to be numbered less than T. So we go up here and stop. If you notice, we're actually following these paths here. But wait, I thought I said I wasn't going to follow these paths. Well, I won't. Let me finish this and I'll explain why I can follow paths here and why I don't want to follow paths over there. So I go to node 4. Node 4 knows its least descendant, so I stop. I go to node 5. Oh, you don't know your least descendant. Okay, set it to equal to 5. And then go to the parent. Well, the parent doesn't know its least descendant either, so it must be 5. And go to the parent, 5, 5, 5, and then find something that's marked, and then stop. And then repeat. So all you have to do is walk up the tree, and here's this. Don't you love that for loop? That's a mouthful, isn't it? It works. So you start, R is where you're walking. So you start at node I, and while you have while you're not a root, so if you fall off the end of the world here, you stop. And while there is such a node, and while the first descendant is not known, walk up the parent, and then, forget this for the moment, and then just set the first of that node to K. There. K, by the way, is if there's a post ordering going on, it's K, not I, that I'm marking it with. Length is useful because I want to. If always computing was the first descendant, I'd be done. There's nothing else to do. So I could leave this out. But I need this thing for the next work, and I'm going to do that next. The other thing I want to do, and I'll come back to here in this tree in a minute. The other thing I want to do, though, is I want to find the level of each node, and the level is going to help us know how long these paths are. Because if I have two nodes in the tree, node A and node B, like this. And I know that node A, I don't want to walk this whole path. But if I have two nodes A and B, and A is at level 10 and B is at level 100, then I know the path is length 90. I can just subtract. I don't have to walk all the 90 nodes. Right? So the level, and I'm trying to remember which direction the level goes. Looks like the level decreases as you go up the tree. And the root of one past the level of a root is 0. Yeah. Okay. So the level of the fictitious node one past the root is -1. And so the levels are going to be, I guess, to say 90 and 10 this direction, or 100? Yeah, so I'm going in the right direction. You could define the levels the other direction, but it's easiest to define the root as level 0. This will have level 1, and I've drawn this poorly. This will have level 2. These nodes... will have level 3. Let's see. These will have level 4, and these I want to have level 5. So that's what I'd like to compute. Now the question is, how do you compute them? Well, there's two ways to compute them, really. You can compute them from the top down. I could have computed this information when I computed the elimination tree in the first place, because remember, I did that from the top down. Right? Not when I computed the elimination tree, when I did the post ordering. When you do the post ordering, you go from the top down. You go from a root and you order all the children recursively. I had to build that head and next list, remember? So I could iterate across my children and delete the list as I went. So I had to go from the top down. I could have done it then, but I didn't. So I guess I'm doing it now. So this algorithm works from the bottom up, and which makes me wonder, gee, why don't I do it in the post ordering instead? But anyway, the book's written, so I can't change it. And so here's the idea. We're going to use these same traversals. On the very first iteration, I started a node and I walked all the way to the root, and I fell off the end of the world. And I found when I did that the last level I saw was -1. And I also computed the length of this path. Because I counted how many nodes did I see. Length plus plus. So I start length equals 0, and I just do length plus plus right there. So then the length of this is 1, 2, 3, 4, 5. The length of this path would be 5. And then what I want to do is, and I hit the root, so forget this first part right here. I did hit the root. I terminated on this condition right here. I fell off the end of the world. We fall off the end of the world, then I want to subtract the length. I want to subtract 1 from the length, if that's the case. And now I want to walk backwards. So I have the number now 4, right? So the length was 5, so I just subtracted 1, so now I have 4, the number 4. Now I'm going to walk this path again and define the levels. So in other words, what's happening here is I came to a place, the end of the world, for which I knew the level, -1. So now I'm going to walk back over this again and mark on this node, oh, you're at level 4. This node, and maybe I'll put a box around the level. This node is at then level 3. And I'll decrement. This node is at level 2, this node is at level 1, and this node is now known to be the root at level 0. And that's exactly what I wanted to compute, to see for those nodes. So you just traverse the path twice. Once to find the length, the second time to mark the levels. Now the other question is, well, what if you go from here and you come to a node whose first is already defined and whose level is then thus also defined? Now, draw a bigger picture here. I have a node here with a known level, and I call this R, node R. And it's known. And I have the node at which I started, which is node I, or the kth such node. So I'm starting at I, and I know the length of this path. Suppose this level is 27. I've got a bigger graph than this over here. And suppose the path length is 10. I'm probably going to count too high here. Maybe make this 5. 3, 4, 5, 6. There, 6. So suppose I traverse this path and I stop here and I found that I went up, I hit a node, I traversed 1, 2, 3, 4, 5, 6 times, and I found that I hit a node R that's not the edge of the world, -1, but it's some node that exists. It's not -1, in which case it has a level that's defined. So what I have to do then is add level to the length of this path. So I'm going to get, see, I want to then define eventually this level to be 28. Put it in a box. This level should be 29. This level should be 30. This level should be 31. This level should be 32. 32 is just 27 plus 6, unless I've done it wrong. Wait. I'm off by 1. Let's see. Oh, I guess the length of this path will be 5, not 6. Because I hit, yeah, it's very easy to be off by 1 in these kinds of loops. So this condition broke the loop. First of R was not minus 1. R is node R at the very top there. There's no name for it except for R. It broke, and so length was not incremented. That only happens at the end of the iteration. So I'm sorry, the length would be 5, not 6, the way I've drawn it here. This is why I'm drawing an explicit example. It's very easy otherwise to be off by 1. So here the length of this path was 5. 1, 2, 3, 4, 5, and then I stop and I don't, that's the edge of the world because it's already known. It's a known level. This length was 5, and so I take 27, add 5 to it, get 32, so that must be the level of this node. And then you just have to walk the path again, setting the levels accordingly, decrementing each time you go up. And so that's what happens here. The length is being decremented each time and then being used to define the level as you retraverse this path. I could have cheated a little bit. I could have gotten rid of, you want to ask, an interesting question would be to ask, what's the shortest number of lines of code and characters in a function even that you can use to explain the function? Okay, I could delete s, the variable s, and I could delete this initialization here and just use I and rewalk, right? Because I don't need I any further. But then that's perhaps confusing because then you wonder, well, I is changing, and I is the node I started at, and why is it incrementing here? And so it'd be a little harder to understand. S is just now temporary walking from I to node R. So little things like that. That in this case, I chose just to make the code a little bit easier to understand than obfuscating it too far. Okay, so this is the first in level. Now, why is it that I can afford to do all this path traversal of the whole tree, but not here, not this k-throw subtree? Well, the reason is this is the entire tree once and for all. But there are n of these. So walking these paths on the one full tree once takes order n time. This is a linear timeout, linear in the number of nodes in the graph, which is the dimension of your matrix. It's not a problem to do it just once. But if I came over here, and for every tree I traversed all these paths explicitly, how much time would I take? You tell me. N times n? No. Too much. There's a better way. There's a better number. How many nodes are in the TK subtree? What does that represent? Non-zeros in row K. What's the time complexity of traversing explicitly every node in this tree? Is it the same or less or bigger? Traversing. If I did this process here just on this subtree, just once, just as an isolated problem, traverse explicitly all these paths, it would take time proportional to the number of nodes in the path, right? Which is the number of non-zeros in the kth row of L. In MATLAB notation, well, I won't use that. Star, comma, k. The number of non-zeros in the kth, column, row of L. Then if I do that for every single row, then the time complexity becomes order L. It's not so bad. And many older algorithms, in fact, did this sort of thing. Okay, but we can do better. If I traverse every path explicitly, then I'm basically just explicitly computing the reach of every triangular solve. Okay, so it's just the sparse triangular solve at each step. It's a tree because I've pruned the graph, remember? And the total time complexity will be order L, non-zeros in L. That's not so bad, but I can do better. Okay. I didn't invent the algorithm, so we can do better. This can be dropped to almost linear time. And the advantage of this is that this is a symbolic pre-analysis phase that you have to do before you can factor the matrix. And you'd like to keep it's, for example, very difficult to parallelize this part of the algorithm. This is a very difficult kind of analysis to parallelize. We'd like to know very quickly, if I just have a matrix and I want to ask, well, how much time would it take, how much memory space would it take to factor this matrix? I'm not actually going to do it. I just want to know how bad would it be if I did do it. Well, then I have to do the symbolic analysis. And that's all I have to do. If you then say, well, it's going to take time proportional to the number of non-zeros in L, then that's actually going to dominate the answer to the question, the time taken to answer the question. Because all you're doing is asking a question, how big is the thing L? If I find the number of non-zeros in each row, I know order L. I know L. I know the number of non-zeros in L is just the sum of all these sizes. And if that's my goal, just to find that, I can compute it one at a time. This one, this one, this one, this one, this one, this one. Or we can do it faster. And we can do it faster if we don't explicitly traverse all these paths. So that's where we're headed. The way we get here is the following trick. We're gonna walk across this tree. And we're going to have a bit of magic. So we've got the reason I did the first Descendant in the level is because to help with this magic. To help with this, magic's a bad word. I don't want to. It's not really magic. It's an algorithm. It's mathematical. It's nothing hidden. Okay. So I don't mean in that sense, but just amazingly subtle. Maybe is a better word. This algorithm. What I want to do is I want to manage to find these intersections. First of all, I want to be sure to ignore these nodes. Okay, these nodes here correspond, and maybe I should put little boxes or something differently here. These nodes correspond to nodes in the matrix A, entries in the matrix A, I should say, which are not in the skeleton matrix. These four are the important nodes. They are in the skeleton. These two are non-zeros in the kth row of A that are to be ignored because they do not contribute to the problem. So they get ignored. So we've got to figure out how to ignore them. Once I have that, now consider this. Suppose I could take pairs of adjacent leaves in the post ordering. This pair, and that pair. And also just this one by itself. So there's really four computations. There's four paths. Let's suppose magically I know this intersection and I know this intersection. I know this node right here. Suppose I have a constant time algorithm. I don't, but it's close. Suppose I have a nearly constant time algorithm just to go poink right there. Find that. So then what can happen, actually I'm going to go by this way. From here I just say, well, I already know the levels here. I know the level of this leaf, and I know who the root is, because the root is k. The root of the kth row subtree is always k, and it is always a tree. It's never a forest. So if I have a node here, and I know its level, I just have to look up the level of node k, subtract, and that gives me the length of this path. Done. Very simple. The tricky part comes in with the next path. But if I could find this node here, if this is node A and this is node B, this node here is going to be called, it's going to be the least common ancestor of A and B. Let's suppose I've got a very fast algorithm for finding the least common ancestor of two nodes. Ask who that is. So this gives say Q. I'll call this node Q. Once I have that now, Q is already accounted for in this path. I have to then take the level of Q, or add 1, because I want to look at just the immediate descendant of Q, and from here, and then that's this path. So if I find Q quickly, I go one level added to that, plus 1, and then I know the level of this node because I have that node and I have its level already pre-computed. Subtract, and I've computed the length of this subpath, this disjoint subpath, in constant time, plus whatever time it takes me to compute this. The same thing here. I go here and I happen to stop just before the root, because the least common ancestor of these two nodes is in fact the root itself. But the root's already accounted for. So I go one below the root here. So this will be the Q of B and C. This is the least common ancestor of B and C. It is in fact K itself. So I take the level of that node, happens to be K, well Q will be equal to K. Add 1 to that, I have this node, whatever that node is. I don't even need to know what that node is, but I know that it has a level of 1 more than the parent. And I know the level of this, subtract, and I've got the length of that path. So on. Okay, so from here, if I find the least common ancestor of C and D, it's this node Q. I'll call this Q1, Q2, and Q3. It's this node Q3, which is the least common ancestor of C and D. Subtract, and we're done. Okay, so we're going to need to know how to find these least common ancestors. But even before we do that, I need to find out where these 4 leaves are, and that's the next algorithm. And all these algorithms are going to be I'm sorry, I said least common ancestor. I mean, I need to find the leaves of the. I need to make sure I know who the skeleton is. What are the skeleton entries? And the skeleton entries are based on the following observation. Once I've got this first descendant, which I just computed, and now I know the level of each node, and I know the least numbered descendant of each node. I've marked it on there. Now I can look at 2 nodes. Okay? And I can look at node 4, for example. I can take any pair of nodes and ask the following question: is someone the ancestor of the other? Quickly, in constant time. Like pick node 4 and node 8. They're not ancestors of each other. Why? Well, look at node 4. Node 4, if I number all the nodes from left to right, 1 to n, node 4 and its descendants will start at node 1, which is the first of 4, f sub 4. And it'll be contiguous up to node 4. The descendants of node 4 are 1, 2, 3, and 4, including 4 itself. Remember, this tree is post-ordered. So I'm talking about the post-ordered names. These are new names, not the old names. What about 8? Well, if I have 8, and I find that the first is 5, I've got two nodes 4 and another node 8. I look at the smaller numbered node 4 and I say, well, if this is less than the first of 8, then they are not ancestor descendants of one another. They're cousins of some kind. They're in different parts. They're not along the same. Neither is along the root. Neither is along the path of the root to the other. In particular, if I start from 4 and I walk to the root, I will not see 8. Yeah.
Instead, you can store the start and finish time of the first search.
Store the start and the finish time of the depth first search.
We have to keep on tracking, like while doing it. If we store the start and finish time of the.
Well, we have the finish time. That's the post ordering. Okay, the start time, though. I'm not sure if that's going to guarantee because I didn't start node 8 right here. Did I? Well, let's see. Maybe I did. Yeah, I'd have to think about that. I'm not certain, honestly. That's an interesting observation. I hadn't thought of that, but I'm not certain if that's the case or not. I have to think about that. So all we have to do then, if we have two nodes T and J, we just look at, and this little diagram means that here's all my descendants, not just the subtree, the kth row subtree, but just in the entire tree. If I have two nodes T and J, and I look at the first of them, either this case will happen, where the first of T is always less than or equal to T, and if T is less than the first of J, then I have that picture I drew up there with nodes 4 and 8. Otherwise, I have this picture. If, on the other hand, the T is, see, here is the case where T is less than the first or equal, well, let's see, less than the first of J. So they're not ancestor or descendants. Here, T is greater than or equal to the first of J. I know already that T is less than J. That's given. If I have two nodes, I can easily find which is the smaller one. So T is less than J. Here, T is less than J. So it's to the left. And here, if you will, it's to the left, but it's actually now inside the subtree for J. Because it's in between. T is less than J, but it's bigger than the first descendant of J. So it's bracketed in the middle. And that would be the case, say, of for example, 9 and 7. Or better yet, let's look at 10 and 7. Look at this node 10 and look at this node 7. The first of 10 is 1. 7 is less than 10, but it's greater than the first descendant of 1. And so what we have here is node 10, and we have the first of 10, which is 1. And 7 now is in the middle. Well, if it's in the middle, if you have a node that is in between the first descendant of the node and the node itself, then you know it's a descendant. Because these are all of the descendants of node 10. They're all packed together in the post-ordering. Right? Any node K and all its descendants are going to be from F sub K to K, inclusive. Plus 1, plus 2, dot, 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 all the way to K. That's what the post-ordering gives us. So it makes for a very easy determination then. If I have two nodes T and J, I can easily tell who's a descendant, if there's a descendant, one is descendant of the other. So then that's going to tell me who these skeletons are. And so if I am at, if I come across here the very first entry, so I'm I'm going to traverse these leaves from small number to large number. Actually, it doesn't actually. Yeah, it does matter. So I'm going to go from these leaves, and that's another question how we're going to do that. But that's another story. Let's suppose I can visit these leaves in a post-ordered fashion. That is to say, if I'm going to see a bunch of leaves, I'm going to see this. Suppose I have one and not leaves. I'm sorry. I'm visiting the non-zeros in the kth row of A. Okay, let's suppose I can visit those entries in post-ordered fashion. Okay, suspend your imagination for the moment as to how we can do that. In other words, I'm going to walk this tree, if you will, from left to right. But anytime I see a node, I want to ask the question, are you in the skeleton or are you not? The way to answer that question is to ask, the first one, it has to be in the skeleton. We're done. But what about the next one? Suppose I've got one here. Then it's let's see. I want this to be true. Oh. I've got this worked out here on an example. And maybe I should just walk through the example and do it that way. That would probably be the easiest thing to do. Let's do it that way. Let's look at T11. Yeah, it's going to be something that's we're going to use these first descendants. And so let me take this tree and I'm going to mark it with the first descendants. So I've already erased them, so let me put them back in again. So there's a tree marked with all of its first descendants. And now T11 is not this entire tree. T11 is going to exclude, it's going to be cut off. All these trees are cut off at some point. So it's a pruned tree, if you will, and it's right here. That's T sup 11. Everything above there. And the entries in A11 to consider are 2, 3, 4, 8, and 10. Almost the entire tree. 2, 3, 4, 8, and 10. The only ones I'm not considering are 9 and 11. But I want 2, 3, and 8 to be determined to be leaves of this tree. Those are the leaves of the 11th row subtree. So to find this, we need to keep track of the largest first descendant seen so far. So I'm going to keep track of a number m, which is the largest the largest first descendant seen so far. And that's with this information, that's going to tell us whether or not this node is a leaf or not. And the trick is, see, I don't want to look at 4 and then look ahead to consider, node 3 or whatnot. I'm going to visit them in post-ordered fashion. So I'll visit 3 first. And then I'll see 4. And then I'll see 8 and 10. So when I'm going to keep track of the largest first descendant seen so far. So it starts out as none. Okay, and I want to traverse across all these entries and ask the question: are you a leaf or not? Are you in the skeleton matrix or not? So the first answer is I come across 2, and the first of that is 1. The first of 2 is 1. So here's a node J, and here's Fj, and this is larger than the one I've seen so far. So this is a leaf. Now I come to node 3, and I see a first, which is 3, and the largest I had seen so far previous to this was a 1. That's the largest first I've seen so far was a 1. This is a 3, and so suddenly we realize, hey, this must be a new leaf, because we have this scenario right here. This first descendant is larger than any first descendant we've ever seen before. And since that's happening, we must have a new leaf. J must be a leaf of the subtree. You notice, by the way, 1 is not even being traversed. It's just being used to help us denote the fact that 2 is a leaf. 1 itself is not being visited. 1's not in the row subtree. Now we come to node 4, and we say, oh, wait, I see that the first has gone down. The largest first descendant I've seen so far is a 3. And so I must have a descendant who I've already visited. In fact, this node. And so this is not new. And we have this situation here, where node 4 is up here, and some prior node who has a bigger first. See, this is bigger than that, because it's inside this group. Because all of these nodes they start here, and they walk through here, and they finish here. This is the least of all these descendants. And if I have a first descendant that's here, then it must be inside this. And so if the first is larger than what I've seen, then if it's smaller, then it's not a leaf. It's this situation right here. So here, this is smaller than what I've seen before. Here's node 4, and I say, wait a minute. This is node 4 must be not a leaf, because I must have somebody inside my subtree who I've seen before in this traversal, because I've already accounted for that descendant right there. And so this is not a leaf, but this is, and this is. And then I come to node 8, and the largest descendant seen so far is 3, but the first of 8 is 5. Ooh. So that's a leaf. That's a whole new branch. It's the root of a whole branch of the entire elimination tree. So that's a leaf of the elimination of the 11th subtree. There's stuff down here that's not part of T sup 11, but the fact that this is first of 8 is 5 says that this is now a unique tree that's different from all the trees I've seen before. And so it's a new leaf. But now when I come to node 10, the largest first I've seen so far is a 5. When I come to node 10, I'm back to 1 again. Well, I know this tree is a tree and not a forest. And so since at this point I've seen, I'm at node 10, whose first descendant is 1. So I have this bracket between 10 and 1. But I know that someone in the middle here has been already seen, because the largest first I've seen is larger than 1. There's a node here somewhere. And so there must be a node here somewhere inside of me that I have seen before. So I can ignore it. In particular, node 8. I've seen node 8 before. This is 10 and this is 8. And the first of 8 is 5. And I've now come across a 1. And so whatever this node is, I don't have to go looking for it, but I know that I must have seen such a node that is a descendant of 10. So 10 is not in the skeleton matrix. So that's the first and the max first. Now, and I have to terminate the lecture here, terminate the path and the search and the lecture at the same time. This gives us a way now of walking across the rows of A one at a time in post-ordered fashion, though, and telling us who's in the skeleton and who is not. So I'm going to use that next class to put all this together and to do the row counts. See you then. Thank you.